1 second. Sorry, it got disconnected. And like I was saying, that we consider this vector as E of A, and furthermore we can therefore we can write that the total angular velocity will be through the 2 points which are at rest, or we can say through the line which are at rest. So there are 2 points A and B. These points are both at rest. So our, you can say, total angular velocity, that is omega, will be along the direction A P prime. We have to remember this part. Therefore we can say that total angular velocity that is our omega will be equal to capital Omega K prime, K unit vector, and omega S, and its direction we have denoted as E unit vector. Okay. And now let us come to the condition of rolling without slipping. So you can say for rolling without slipping, and for that let us consider a vector from the apex point A towards the contact point P prime. Okay. You can say vector from apex A to contact point P prime, and let us call that vector as R of C. Therefore the rolling for rolling without slipping condition, we can write that our omega cross R of C should be equal to 0. Okay. And moreover, we can also say that the vertical plus the axial component must combine along the slope. Okay. We can just draw a conclusion from there, and therefore we can write that our capital Omega plus our spin velocity and the dot product of two unit vector should be equal to 0. And the dot product of these two unit vector, this EA and our K unit vector, we can write that will be equal to our cos of pi by 2 minus alpha, or we can write this will be equal to our sine of alpha. Okay. And we substitute, and therefore this gives us that our plus omega s sine of alpha is equal to 0, or we can say our spin velocity will be equal to minus omega, which is our precision velocity, should divide by sine of alpha. And if we substitute value of omega we already know is our v upon h cos of alpha. Therefore we can write that omega of s is equal to minus, and this comes as v, and we have our h cos of alpha divided by sine of alpha. Okay. Now, but we are interested in finding out the total angular velocity, which is our omega. Therefore, we can say that the total angular velocity which is omega is equal to our omega k unit vector plus omega s, and we have here e unit vector. But we already know that our dot product of this is equal to sine of alpha. Okay. So therefore we are interested in magnitude only. Therefore we can say that the magnitude of this omega will be equal to omega cot of alpha. But we already know this omega is equal to v upon h cos of alpha. So we can write this as our v h cos of alpha times cot alpha. Therefore cot alpha we can write cos upon sine, so cos is going to cancel out. Therefore we get that the magnitude of is equal to v upon h sine of alpha, which was our required question. Okay. So this was the first question. Now we come to the second question, and okay, so in this second question it states that a fixed cone stands on its tip with its axial with the axis vertical. The half angle of the vertex is theta. A particle of negligible size slides on inside frictionless surface of the cone. See figure. Suppose the conditions are arranged such that the particle moves in a horizontal circle at a height h above the tip. Determine the frequency omega of this circular motion. And part B, now suppose the inner surface of the cone has a friction and a small ring of radius r rolls without slipping on the surface. Conditions arranged are so that the point of contact between the ring and the cone moves in a horizontal circuit of height h. The plane of the ring is always perpendicular to the line joining the point of contact to the tip of the cone. Okay. And in this case also, find the frequency omega of the circular motion. You may work in the approximation that r is very much less than h tan of theta, so that the ring is much smaller than the radius of the circular path. Okay. So in this case, we are given that we have cone and that cone is vertical. Okay, that's the basic question. And so let us draw the basic figure. So we are given that we have a cone and that cone is vertical. Okay. So this is the base of the cone, and let me draw it a little bit larger. So this is the base of the cone, and in this cone we have a, you can say, in the first case we are given a particle of negligible size. Okay, so we have a particle, suppose at this point, and it is moving the circle. And we are also mentioned in the question that this particle is moving a circle at a height of h, and let us suppose, and half angle is given as theta, and so let us suppose r is the radius of the circle. Therefore we can write that our r will be equal to h tangent of theta. So it means the horizontal circle is going to have a radius of h tan of theta, and suppose it is moving with angular speed of omega. Therefore we can say that for angular velocity of omega about the vertical axis, and one second, for the angular speed, for the angular velocity of the vertical axis, so let us call this as omega, and from here we can find out that the speed of the particle, or you can say speed of particle, suppose that is given as v, then this v is equal to omega times r. So means we found out the relationship between v and r, which is our basic relationship. Now we come to the part A, and part A, it states that the surface is frictionless, and we are supposed to find out the value of the frequency. That's our part A. So part A, we can draw the various forces. So this is one of the slants of the cone, and at any given moment, suppose this is the particle, therefore in the downward direction we are going to have our mg, and we are given that its angle, half angle, is given as a theta. So this will be our theta, and there will be also a normal force rather, that will be acting perpendicular to the slant. And we can divide this normal into two components, and so we have this as theta, so this will be over 90 minus theta, and this will be angle theta. Therefore we can say this comes as our n sine of theta, and this will be coming as our n cos of theta. And for the balanced forces, we can write the equation. So we can say our balanced vertical forces we can write that our n sine of theta is equal to our mg. And for our, you can say, there will be also a centripetal force, and this n cos of theta, or the component of n, is going to provide it. Therefore we can say that the centripetal equation or we can also call it a radial equation, this can be written as our n cos of theta is equal to our mv square, and v we already know is our omega times r, so we can directly put it here, and mv square upon r, so that will be coming as m omega square r. So let us call this as equation number 1 and equation number 2, or simply we divide them, and second divided by first will be giving us our n cos of theta divided by n sine of theta will be equal to our m omega square r, and we have this as our mg. Here this normal and mass cancels out, therefore we can write that our cot of theta is equal to omega square r and divided by g. But we know that our r is equal to h tangent of theta. So we know that our r is equal to h tangent of theta. Okay. Therefore, we can write, because we required this omega, so we can say our omega square is equal to, we get this as g cot of theta divided by r, and we can substitute value of our r, that is our tangent of theta. Therefore we can write this as our g cot of theta, and r is our h tan of theta. Okay. And this is basically 1 upon tangent theta, that will be equal to cot theta. Therefore we get that omega square is equal to g upon h, and we have our cot square theta. Therefore we get our omega is equal to our cot of theta square root of g upon h. This is our frequency, and when the surface is frictionless, and that is a very small particle. And now we come to our part B. And part B, we are given that there is a ring, okay, and suppose the ring is having a radius small r. We can say part B is our small ring, and we assume that its radius is small r, okay, and so let us write. So we assume that our omega, it's the angular frequency of the center about the vertical axis. Okay, so omega is the our angular frequency of the center of ring about the vertical, whichever we are required to find out. And this capital omega, because the ring will be also, because there is a friction, so ring will be also rotating about its own axis. Okay. So we call this as a spin angular speed. Spin angular speed of the ring about its own axis. Its own axis, and sometimes this axis of this ring we can also call it as a generator. And I is the moment of inertia of the ring about its symmetric axis. So moment of inertia of ring about symmetric axis. And for which we have a standard formula, that is our mr square. And we can furthermore write this as now we come to our no slipping condition. So we have our no slip condition, and under no slip condition we can write that our, one second, yeah, one second, I just made a mistake. Let me correct this part. We have small ring and whose center of mass moves in a circle of radius RE. Okay. So it basically means that, let me draw it here. So we have a cone and we have a ring. So I'll draw a ring on the larger side. So this kind of ring is there and its center of mass is moving in kind of circle. And this circle is said to have a radius of RE, and this ring is having a radius of R. Okay. And it is given that this R and the radius of the ring is very small, such that this radius is approximately equal to our R, which is nothing but our h tan of theta. So I'll come to that later on. And therefore we can write, for no slip condition, our omega times RE should be equal to omega times capital Omega times R, and which basically means that the tangential speed of the ring's center of mass equals to the tangential speed of the ring surface at the point of contact. Okay, this is the meaning of that. Let me put it here. Okay, because at any given instant we can say that the point of contact is momentarily at rest relative to the cone. Therefore we can write that tangential speed of the ring center of mass equals tangential speed of ring surface at point of contact. And we can also write the equation for the ring spin angular momentum about its own axis. So you can say that spin angular momentum of ring about its own axis, and let us call that L. So L will be equal to our I omega and L unit vector. Okay. This unit vector is our along the generator. Okay. Like I said, the generator is nothing but over the axis point, axis line basically. So you can say our L unit vector, this is a unit vector along generator. And from here we can find out the magnitude of rate of change of this angular momentum. We can say that magnitude of a rate of change of L, and this will be nothing but our dl upon dt, and we can write its formula, that is our dl upon dt will be equal to our L omega sine of theta. Sine of theta. I think it again got disconnected. Doesn't look like. Okay, let me continue. We'll see that later on, and which can be further written as our L, not L, sorry, I omega sine of theta. Okay. And therefore, okay, this was the first part, and the second part we come to the friction, and our friction will be, you can say, producing a torque, and therefore we can write that our say that our friction F produces a torque, and we can write that torque is our tau, which will be F times R. And obviously we can equate this to our rate of change of angular momentum. Therefore we can say our F times R will be equal to our I omega sine of theta, and we know that our moment of inertia I is our mr square, and our omega is equal to omega Re upon R. Yeah, from here we can calculate it, and therefore we get that our Fr is equal to mr square. This is omega Re upon R, and what is left? Omega is left, and we have our sine of theta, and this R goes by our square, and this R cancel by R. Therefore we get our frictional force will be equal to over m Re, and we have this as omega square sine of theta. This equation we can use later on for the frictional part. Okay. Now let us divide all the forces inclusive the frictional forces. So we have our, this is the slant of our cone, and we have our ring somewhere here. So we are going to have a mg in the downward direction, and this angle is given as theta, so this angle will be also theta, and we have a normal, and we can divide this normal into two components. This angle will be also theta, so we get this as n sine of theta, and this will be n cos of theta. And this, we come to friction. So friction will be acting in this direction, and we can divide this into two components. So we get this angle will be over theta, so we get f sine of theta, and here we get our f cos of theta. Okay, so these are the various forces, and now it is quite simple to solve. Okay, so we can say for vertical balanced force, you can say for vertical balanced forces, we can write that our n sine of theta plus f cos of theta is equal to our mg, and from here we can write that our n is equal to our mg minus f cos of theta divided by sine theta. So this is our normal, and because of the radial component, that is going to provide the necessary centripetal acceleration. Therefore we can say for horizontal balanced forces, we have two forces, but both are in opposite direction. We have n cos of theta and f sine of theta. Therefore we can write that our n cos of theta minus f sine of theta is equal to our m omega square times our Re. Okay. And now it is quite simple solution. We got all the equation, we already know value of n, so we are going to put it here. Okay. Therefore we get that our mg f cos of theta, mg minus f cos of theta divided by sine of theta, and multiply by cos of theta minus f sine of theta is equal to m omega square Re. Okay. And we are going to rearrange the equation because we have a f component here and f here as well. So we are going to solve it by multiplying the sine of theta, and we get this as our mg minus, we will be getting this as cos square, so f we can take as common, so this will be coming as a cos square of theta minus sine square of theta, and one second, it's minus or plus. Okay, so we can take minus outside, so this will be a plus, and equal to m omega square re, and this is our sine of theta, and this cos square plus sine square is equal to 1. Therefore, we get that our friction, that is our F, will be equal to, we can write this as our M, we can take as common, and we get this as our G. One second. F. Okay, yeah, this is 1. So it comes as a M, and we have our, I think I missed something. Yeah, I missed one thing, that is cos of theta. So we have this as mg cos of theta. So we get this as our g cos of theta minus, we have our omega square re sine of theta. Now we are having two equations of our friction. Okay, let us call this equation number 1, and this is our equation number 2. So equating 1 and 2, from first and second, we get our m, and this is our g cos of theta minus omega square re sine of theta is equal to m re omega square sine of theta, and m we can cancel out immediately, and we are going to combine the terms of our omega square. So we get this as our g cos of theta will be equal to, and this is our, okay, we can add them, so this will be coming as 2 omega square re sine of theta. So now it's almost done. So we get this as our omega square is equal to g cos of theta divided by twice re sine of theta. But we are also given an approximation. In the question itself, we are given that our re is very much less than our h, very much less than our h tan of theta, and h tan of theta is nothing but our r. Okay. Therefore, we can straightforward very much less than our capital R, which is our h tangent of theta. Okay. So we can write that our omega square is approximately equal to g cos of theta, this comes as 2 sine of theta, and in place of re we can simply put h tan of theta, and h tan of theta will be equal to our sine upon cos. So this will be coming as cos square upon sine square. So this will be over g upon 2 h, and we get this as our cos square theta and sine square theta, which is nothing but cot. Therefore we can write our omega is equal to cot of theta square root of g upon 2h. So this is our frequency of a small ring that is rolling without slipping. Okay. And if we make a comparison for with respect to first part we got that omega is equal to cot of square root of g upon h. So this was the answer for part A, in which we have taken the particle and there was no friction. So for comparison we can say there is a, you can say, I think, let me check, yeah, g upon h. Okay, so here it comes 1 by 2, so there is a factor of 2. Okay, so we can make a comparison between the two also. Rest of the things are same, only the variation is there is extra factor of 2 within the square root in case of a ring, which is consisting of the friction. So this completes all the 2 questions. Thank you.